Good morning, and thank you for the opportunity to talk about my work on porous media modeling of cell expansion in hollow fiber bioreactors. In my talk today, I'll begin with an introduction to the motivation and aims behind this work, some background on hollow fiber bioreactors. I'll discuss how the porous media model is set up, highlight some key results, and some concluding remarks, and leave time at the end for questions. To begin with, the motivation behind this work is primarily the hope that CapEx's contribution to the cost of production could be reduced through process intensification. And some ways to intensify the cultured meat bioprocess from a bioreactor standpoint includes continuous rather than batch cell harvest from bioreactors, increasing the bioreactor maximum cell density, and increasing the number of exponential growth doublings per bioreactor. And hollow fiber bioreactors are the focus of this work because they show promise in supporting process intensification due to their ability to support in vivo-like cell densities and support 6 to 7 exponential growth doublings. However, there are knowledge gaps around the scale-up of this bioreactor design, and therefore the aim of this work was to use the porous media model to predict theoretical scale-up and productivity constraints for cell expansion in hollow fiber bioreactors. So some background on hollow fiber bioreactors. This bioreactor design is based on bundling several hollow, permeable membrane fibers together inside of a bioreactor module. And the space inside the fibers is called the lumen, and the space outside the fibers is called the extracapillary space. And as shown in this diagram, typically media is perfused through the fiber lumen, and cells are seated in the extracapillary space. A common approach to modeling the hollow fiber bioreactor is the Krog cylinder model, which is based on the simplifying assumption that a single fiber is representative of the entire bioreactor. And this model is really well equipped for looking at nutrient delivery and waste removal to and from the cells in the extracapillary space, and how it depends on media perfusion rate, fiber geometry, membrane characteristics, and the cell layer thickness. But this model is not well equipped to look at what happens as you bundle these fibers together and scale up your bioreactor radially. The porous media model, on the other hand, can answer that. It is a common approach to modeling the hollow fiber bioreactor as a whole, and has shown this 2D spatial domain. It is able to capture the effects of bundling your hollow fibers together. The porous media model is based on the idea that your hollow fiber bioreactor can be treated as two distinct and separate porous media, where the lumen side porous media consists of pores that are the fiber lumens, and the membrane in the ECS is considered the solid region. And then on the shell side, you have a porous media where the pores are the void spaces between the cells, and the solid region is the fibers and the cells themselves. The two regions are coupled by pressure-driven transmembrane transport from one region to the other. All parameters used in this work were taken from a commercially available hollow fiber bioreactor from FiberCell Systems. And to be clear, this diagram highlights the concept of splitting a single bioreactor into two distinct regions. So this is one bioreactor showing how the lumen side region has its own distinct porous media parameters and boundary conditions, and the shell side region also has its own corresponding set of parameters. In this work, one of the ECS ports was opened and set to a reference atmospheric pressure, and the reason for this was to explore the impact of opening the ECS port and its expected benefits, convective mass transport benefits. The lumen back pressure was calculated iteratively in order to maintain a volumetric flow rate out of the lumen to volumetric flow rate out of the ECS port flow rate ratio of 3, as shown in this diagram. And finally, the variable that was varied throughout this work was the porosity in the ECS. And this equation just highlights that as your cell density in the ECS goes up, the porosity goes down because the porosity is the void spaces between the cells. So one of the key findings from this work is that high cell densities prevent the extracapillary space port boundary condition from propagating throughout the ECS. So going from top to bottom, these plots show the steady state pressure profile in the extracapillary space for increasing cell densities and corresponding decreasing porosity. And the dark blue purple is essentially the 101 kilopascal boundary condition that was set at the ECS port. And you can see that at low cell densities, that is distributed throughout the ECS, but at high cell densities, it doesn't propagate very well through the ECS. And what this is showing is that essentially the cells result in a plugging effect in the ECS. And at high cell densities, the ECS pressure becomes increasingly dependent on the lumen pressure and less dependent on what the ECS port boundary condition pressure was set at. And what this translates to is that high cell densities effectively eliminate the convective mass transport benefits expected from opening the ECS port. So at low cell densities, you can see that the velocity profile is pretty well distributed throughout the ECS, and that encourages convective mass transport throughout that region. But you can see that at higher cell densities, the ECS flow becomes increasingly concentrated at the port. And the other thing to highlight is that the lumen back pressure that was iteratively calculated in order to maintain the target flow rate ratio, you can see that at higher cell densities, you have to back pressure the lumen more, which does make sense. You're trying to force more flow out of the lumen and into the ECS region, but back pressuring cannot be used to better distribute the velocity flow. You just get higher velocities distributed around the ECS port. And one more thing to highlight is that I then looked at closing the ECS port and instead setting the lumen back pressure to a reference pressure of atmospheric again. And what this highlighted is that you do see the anticipated Starling flow at low cell densities, which is when flow leaves the fiber lumen for the first half of the fiber and then returns to the fiber lumen in the second half of the fiber. But even this form of convective transport is expected to disappear at high cell densities as the cells plug up the space. And what this means is that as you scale up, and as you see higher cell densities, the convective mass transport in the hollow fiber bioreactor is expected to completely disappear. And this means that you're going to be diffusion limited. And this directly impacts the possible thickness of the cell layer that can be supported around each fiber. So this plot just shows the fiber packing density for different cell layer thicknesses around each fiber and for different sized fibers. And the point highlighted is just the system that was modeled throughout all this work, where 42% packing density corresponds to a cell layer thickness of about 76 microns. So key conclusions from this work are that hollow fiber bioreactors' potential to support in vivo-like cell densities is anticipated to come at the cost of convective mass transport in the ECS. And what this means is that diffusion-limited mass transport, rather than having convective enhanced transport, requires more bioreactor volume to be allocated to the fibers. Some future work in this area is that the porous media model can be used to investigate heat transfer and investigate radial scalability further, because this model is well equipped to look at radial scale-up and the impact on the effectiveness of heating or cooling jackets on the outside of the bioreactor. And finally, this work can also be used to compare the cell expansion in hollow fiber bioreactors to additional process intensification options, such as continuous versus batch cell harvest. And with that, thank you very much for listening, and I'll take any questions.
Thank you so much. Questions? Yeah, Mark.
Thanks, Lily. Wonderful presentation. In how far is cell proliferation actually a parameter in this? So in other words, if you do, as you know, some of them are developing these hollow fiber bioreactors for differentiation, where there's more a steady state of metabolism in the cells. How far is that important?
So this just looked at, like, as you increase the cell densities at steady state, what at each cell density, what the pressure and velocity profiles look like. I would expect that cells begin to differentiate. You will already have reached a very high cell density, so you would expect that the reactor is quite plugged up by that point.
But are you assuming throughout the length of the hollow fiber that cell proliferation is the same and cell density develops in the same way?
It is based on the assumption that cells are distributed evenly in their perfect spheres throughout the entire ECS.
Okay, so it's just homogeneous
Yeah.
cell density across the bioreactor.
Yeah,
Right.
yeah. It treats it as a homogeneous porous media.
So that shouldn't affect actually the flow pattern.
The you mean differences along the axial length? Or-
Right.
No, that is not accounted for in this model.
Okay. Okay.
So I don't know if I understand this correctly, but so if it becomes diffusion limited, that includes oxygen and nutrients. That's what you're referring to?
Yeah, so it's just highlighting, there have been models that look at like opening up the ECS port or inducing intentionally having Starling flow in order to have better convective mass transport to the cells. And this is just highlighting that at higher cell densities that will disappear. So
Right,
yeah,
and
transport of oxygen to or any waste metabolites away from.
And so as you go along the fiber, oxygen can become even more limited as it gets used up. So I mean, can you people have put in like oxygen carriers into these sorts of things. Have you thought about that? Like, would that make a difference at all?
Yeah, so I would say that this model mainly just wanted to highlight that I would say that Krog cylinder modeling is very well equipped to answer that kind of question, and that the cell layer thickness is something that can be looked at from a Krog cylinder standpoint. And so this model is just highlighting that when you're looking at the Krog cylinder, you shouldn't take credit for convective mass transport benefits. And so if you're using carriers,
But yeah, it's operating under like basic assumptions of like oxygen solubility in media. But if you increase that, then it could go further, maybe.
yeah, so you could have a higher cell thickness layer if you had that, yeah.
So, okay, final.
So just for my understanding of the system, because you mentioned eventually you would want to go to continuous harvesting as well, but the cells grow on the fibers, so how do you get them off again for the harvest?
Yeah, so this was just, that point was mainly to highlight that that is another approach, non-bioreactor specific, so not saying specifically that we would try that in hollow fiber bioreactors,
Okay.
but just that it's another way to intensify your bioprocess.
Okay, yeah, thanks for the clarification.
Thanks.
So thank you again.